All right, let's talk about this idea of static equilibrium. Static equilibrium means an object has no linear, meaning left, right, up, down, or back and forth. So in the x, y, or z axis, it has no linear or rotational acceleration, aka it's not speeding up or slowing down in a spinning manner, if you will. All right. So in other words, F equals ma, Newton's second law, your acceleration must be 0. Now, there's another equation that I'm not going to worry about deriving for you that it looks exactly the same, and it deals with rotational. This is torque, right? Sum of all the torques equals, this is the moment of inertia. Moment of inertia is related to the mass, how large the object is, and basically it tries to get the idea of how the mass is distributed inside of an object. So it deals with, is it all lumped to one side or the other? Because that will obviously affect how it turns. Or is it all spread out towards the outside, or is it evenly distributed? You know, what's going on here? But this is kind of like mass in there. And this alpha is angular acceleration, right? Angular acceleration. So no rotational acceleration or angular acceleration means this has to be 0 as well. Right now, we're not going to talk about your moment of inertia nor your angular acceleration. We're not going to solve through those just yet. But what that says to us here is if static equilibrium, no linear, no rotational equilibrium, all of my forces have to sum up to be 0, and all of my torques have to sum up to be 0. Now, where we're going to start out right now is only dealing with the torque part of it. We're not going to worry about the force part of it just yet. We'll come back to that maybe later. But some of my torques has to be 0. In other words, the thing shouldn't be rotating, right? The thing shouldn't be rotating. This does leave a kind of a window, static equilibrium. If you're not accelerating anyway, you could be moving at a constant velocity, meaning that I could be moving at a constant velocity in left, right, x, y, or z axis, or I could be rotating at a constant velocity, but I can't be speeding up, slowing down, turning in any way because that would imply an acceleration there. So everything must remain constant, okay? Let's see. Another thing that I need to talk about is center of mass. Now, center of mass is a location on an object where all mass can be reduced down as a point mass. In other words, if I have, let's say, a large kind of pole here, ruler, meter stick, whatever it is, that mass is distributed throughout it. The center of mass is the point where, if you will, it would balance, right? Where there's the equal amount of mass on the left is on the right if you like put your finger under it or something. It's the point where if you were to start shrinking all the mass down, it would reduce to that spot. If mass is evenly distributed, meaning that it's not all clumped to one side or the top or the bottom, things like that, one side isn't more dense than the other, the center of mass is always going to be in the center of the object, right? On the other hand, if it was, let's say, not evenly distributed, let's say the left-hand side of this thing was a little bit heavier than the right-hand side of this thing because the left-hand side, it was more dense. Maybe this piece over here is metal or something, and the rest of it's wood. Well, that would mean the center of mass would shift a little bit. It would become closer to that side, right? That would be the balance point there, or where if we were reducing all the mass, the spot where we could reduce it all down to pretend it's a point mass at that location. That's the center of mass. I do want to talk for a brief moment about this idea of rotational acceleration and then get off of it because it's not something we're going to use right now. We might come back to it later. Every linear thing that you're used to, like for example, displacement, right? So displacement delta x, right? Displacement has a partner, right? His partner would be in rotational terms delta theta, or change in my angle. X would be theta, same thing, right? I'm changing an angle here. By the way, the angle, and if you're dealing with rotational stuff, you're going to need your calculator in radians. It's a lot easier. Everywhere else we like degrees. In rotational, though, radians becomes a lot easier. Velocity also has a partner. His partner is omega, or rotational velocity. How fast are you spinning? Okay. And then acceleration has a partner, alpha. how are you speeding up or slowing down rotationally, your rotational acceleration. And if you ever want to get between the two, if you ever want to be able to convert between the two, right? If you know a tangential velocity or a tangential displacement or anything, all you have to do is multiply by r times your rotational, and you're back to tangential. So that's the idea here if you ever need to convert. But like I said, that's not something we are necessarily dealing with right now. Now, as for actually solving rotational equilibrium problems, static equilibrium, but only dealing with the torque. So sum of my torques equals 0. That's the equation that I'm going to cling to. Add up all your torques, taking into account direction, positive and negative, set them equals to 0, solve for what you need. So steps: draw a picture. 2, choose a rotation point. That's critical. Make sure to try to choose a wise one. Choose one that's going to occur in reality. If you're having a problem that's more complex that would involve you've got to sum up the forces for later on, you're going to want to choose a rotation point that is going to take a torque away from you so you don't have to worry about it. But you'll see if you're just using, if all you have to do is rotational, there's going to be a point that you know it's going to rotate in reality. Choose that point. That will be the easiest one. Choose positive and negative for your rotation. In other words, if it rotates clockwise, positive, counterclockwise, negative, or vice versa, because that's the sign, positive, negative, you're going to have to assign to your torques. Find the center of mass of any object, right, that's necessary. If there's a balance beam or something else, a wheel that's turning that has mass that you have to deal with there, find the center of mass. Another point that I should make, if the thing is rotating about the center of mass, it won't matter. Okay, if it's rotating about its center of mass, it won't matter. 5, find the distance between any of the forces and the rotation point. So how far away are the forces from the rotation point? More than likely, those distances won't be explicitly given. It'll be something along the lines of they tell you the length of the entire beam and you pick a rotation point, and then just using basic subtraction you figure out the distance between forces and rotation point. Sum up all the torques, so label your picture and then sum up all your torques equals 0. Break down the forces if necessary. Remember, torque, right, is when torque is your R, F, sine theta, and sometimes F will have to get broken down. The most common thing is the force that's applying the torque is actually Fg, which then would break down into mg. So you'd have R, mg, sine theta. That's one of the most common ones that you'll see occur where you have to break it down there. And then solve for your unknown. All right, so let me talk now for a moment about center of mass. Try to clarify that some. All right, so moving pretty quickly on the center of mass idea, assuming that these two objects have their mass distributed equally, I can assume the center of mass is in the very center. That means it's as if all the mass would be brought into one point, or a point mass, reduced all the way there. The object will behave rotationally like all of its mass is put right there. Meaning that if I put, let's say this little plank is actually a seesaw, if I put my logical rotation point, a fulcrum, right there at the seesaw, or right there at the center of the mass, this thing would balance perfectly. But if I change that, if I put my fulcrum, let's say, off to the side, right, now I have a distance, I'll label that R, between my rotation point, which would logically be right here at the fulcrum, right, and the center of mass. Meaning that here is a torque, right, because of the center of mass, and this thing is going to rotate like that. Likewise, over here with my wheel, if you will, pardon the pun, please. The center of mass would be at the very center. So if I just put this, let's say, on a flat surface, right, force of gravity going straight down, as long as that point is at the very center, nothing's going to happen, right? The wheel will just sit there. If it was perfectly, if the center of mass was perfectly at the center because mass was distributed evenly. But what about a wheel starting to roll off a table? So if I have a table here, right, that comes over like that, as soon as that center of mass gets a little bit off the table, that wheel is now going to rotate, causing it to turn and then obviously fall off the table there. So in other words, if your rotation point is at the center of mass, the mass of that object, assuming that whatever it is has mass, isn't going to provide a torque. You don't have to worry about it. On the other hand, if it's offset, now I actually have a distance. If my rotation point is offset from the center of mass, now I actually have a distance r, like here would be my r, right? I have a distance r between the rotation point and the center of mass, meaning that now I have mass, which is a force, right? Force of gravity is what's going to occur. A distance, that's a torque. So then I have to account for the center of mass in my torque problems. All right, so we're going to work a static equilibrium problem for you that only has to deal with torques, rotational motion, not having to deal with forces in linear motion. So it's a standard diving board. I have here a person at the very end of my diving board. Over here, right, diving board attached with two bolts to some sort of support there, right? The entire board is 2.75 meters long, and the length of the support is 0.75 meters long, and then you're over water. Now, I need to choose a rotation point, and I'm going to make sure to choose that wisely. And my rotation point I'm going to choose is going to be the front of that stand or support, because that's the part it would spin on. If this person, if all of a sudden these bolts at the very back that hold the board down snapped, the board would rotate like this around this front point right here, more than likely. So I'm choosing my rotation point here. My question for us to solve is, how much force does these bolts have to apply downwards? How hard do they have to hold on? If I have a 75 kilogram person at the end of the diving board, it makes logical sense. And I also have a massive diving board, 59 kilograms. How hard do these bolts, how much force do these bolts have to apply? Next thing that I need to do is go ahead and choose system positive, system negative, or rotational positive, rotational negative. I'm going to choose everything that makes the board rotate this way as positive, and I'm going to choose everything that makes the board rotate that way as negative. And it doesn't matter which way you choose, you just have to choose and then be consistent for the entire time. All right, so sum up my torques, right? Sum of my torques is going to equal to 0 here. And let's maybe deal with that here in a second. I also need to figure out distances and label my forces. So the person at the very end of it is going to have a force of gravity, right, because of the person. So I'll do force of gravity, maybe P for person. Also, I have to find the center of mass. Now, the center of mass of a diving board, assuming that it is nice and evenly divided up, right, the mass is distributed completely evenly, the center of mass is going to occur somewhere in the very middle of the board. So right here, right in the middle here, okay? So I'm also going to have a force of gravity because of the board pulling down, right, Fg of the board, right? And then I'm going to have a force of the bolts. Now the bolts idea is it tries to hold the board down also. I'll label that just FB, force of bolts. It's trying to pull that side of the board down to not let it rotate. I also need to figure out all of my distances because that's going to be needed in my torques. All right, so this distance right here, what would that be, okay, from my pivot point out to my center of mass? Well, if the center of mass is at the very center of the board, that means this length right here is 2.75 divided by 2, which is 1 point, let's see if I can't write it in there, 1.375, 375, okay? Now, if that entire length right here is 1.375, and this point right here is 0.75, 1.375 minus 0.75 will give me this part right here, which is 0.625. So 0.625. Okay. I also need to know the distance from the pivot point out to the person, or the force of gravity of the person. If the entire board is 2.75 and this part is 0.75, that leaves this length out to the person to be 2 meters. Now, I know all the forces, or I know these two forces and looking for this one. But I know all the forces that are acting, the direction they're acting. They're all acting at 90-degree angles because they're going straight down and the board is horizontal. I also know the distances of all those forces from the pivot point. Force of center of mass is going to be 0.625 meters from my pivot point, which I chose to be the front of that stand. The person's force is 2 meters away, and the bolt is applying it 0.75 meters away. So I'm ready to sum up my torques now. Sum of the torques equals 0. That's going to make it where the board doesn't rotate here. In case you haven't noticed, when doing this problem with torques, because you have to figure out a lot of distances for static equilibrium, drawing a picture and labeling it and working through is probably going to be mission critical here. All right, so everything that causes it to rotate positive, let's write that first. First off, the torque because of the person is positive. It's trying to make it rotate that way, right? Also, the torque because of the center of mass, I'll label it torque Cm, center of mass. Once again, that's trying to make it rotate positive. Minus the torque because of the bolts, that's trying to make it rotate in the negative direction. So if somehow or another these bolts were able to push all the way through and that force became large, it would rotate it that way there. So those must equal 0. Now let's break those torques down. Thankfully, the angles are 90 degrees, so since all the angles are 90 degrees, I can drop off the sine theta part completely. So this becomes R to the person, and the force that's going down is the force of gravity of the person, right? Plus, now the center of mass, RCm, times force of gravity of my center of mass, minus the force of the bolts, which is my goal, that's what I want, times the, and let's actually flip-flop that per the equation that we have, the distance to the bolts times the force to the bolts, and FB is what I want. All right, now I can break all those force of gravities into mass times gravity here, and then plug in numbers. So once again, just took my force of gravity, let's say of the person here, and broke it down to mass of the person times 9.81. Same thing here with the mass of the board, right? Since it's not at the pivot point, the center of mass isn't. The board itself would be trying to rotate. That's why it's having to be included. So force of gravity of the board, mass of board times 9.81. Now let's plug in some numbers. And with significant figures, I end up with 2,400 newtons is how much force these bolts have to apply downwards, right, to hold the dive board, to prevent it from rotating off and our person falling off into the water unexpectedly.